Yes. So, what should I say? So now we will look at the yield. And actually, the yield and productivity is one of the most questions I receive usually is like, can you do the yield? Can we estimate the yield? Can you forecast the yield? And I say, yes, I can, but Natasha, no. No, very well, and she is our expert in doing this, and like she's the our like let's say reference in doing the yield estimation. Um, Natasha is an assistant research professor in the University of Maryland, and she works also in collaboration with Acres and NASA Harvest. And today we want to learn more, and she will be presenting as more satellite-based DL estimations. So, Natasha, the floor is for you. Thank you so much, Natasha.
Yeah. Thank you, Walid, for the introduction, and hi, everybody. I'm happy to be here and talking about satellite-based yield estimation. So first, why do we want to predict the crop production action? So the main goal is to ensure that the consumptions align with the production, basically. So, because when this balance is disturbed, it can lead to market instability and significant price volatility, like you can see on this little figure on the right. So as you can see from this chart, I can maybe play it again. That it shows a corn yield anomaly between 2001 and 2021 over the USA at county level. So the anomaly around the trend, and you can see huge variability from a year to another and from a county to another, which finally makes to have an accurate yield forecasting very challenging, especially when you move from national level to thinner spatial resolution. So what is the challenge of yield forecasting? So it's hard to build a yield forecasting model because it depends of the space and time of your scale. So like you can see on this figure on the right, you can see the yield over a field of a corn yield, actually over a field in Iowa. And you can see that when you aggregate this yield that is at 3 meter spatial resolution until 30 meter spatial resolution, you decrease the yield variance drastically. So you can imagine now if we upscale again from a field to a subnational level until national level, what are we predicting? What kind of yield do we want to predict? So we have to ask ourselves the question, what spatial scale do I want to look at? And for that, it will depend of what kind of method and what kind of data you will be able to use. Like, for example, if you want to look at very field level, you will look at you will use, for example, LiDAR, radar data, or airborne data. Or if you want to look at more global yield or subnational level, you will use satellite remote sensing data. The same way, some parameters influencing the yield at field scale, like disease or the soil texture, will have a very important impact at that scale, but less important impact at county level, while a big drought event or frost at the beginning of the spring will impact a regional scale. So very quickly, the first step before creating a yield model, it's if we want to use satellite data and especially optical data. So the first step before all of that is to correct the signal from the satellite from all the scattering and absorption effect due to the atmospheric component. So in my team, so SALSA team, my colleague, I've been working for that for many decades actually. And I built some aerosol model and atmospheric radiative transfer model. So I just added the QR code if you're interested of working on that. It's free, you can download it and it's documented. If you want to add a new satellite data or some information on how it is done, feel free to contact us. So while you have a signal corrected, you can estimate the surface reflectance. And so you have a huge variety now of sensor with a different spatial resolution, like MODIS or VIIRS are with grosser spatial resolution, like around 500 meter. And you have also like very high spatial resolution, will be like more commercial satellite data, like planet data. So a part of them are already corrected from the atmospheric correction and also the BRTF effect. And you can download this data on different platforms. And I just add two of them, like maybe the most commonly used, like Earth data, NASA, and Copernicus dataset. So now that we have clean signal from the atmosphere, we can build a yield model. So how we do? So there is different type of yield model possible. So I will say there is the first big general yield model will be the crop growth model, so physical based model, like you have some, for example, EPIC or APSIM. So this kind of model are very flexible and very great to do some kind of sensitive study on the yield impact of some parameters, because you can actually play with the model. Like I think in EPIC there is like 100 possible parameters as an input, but that makes this model not very straightable when you want to do operational or when you want to look at a huge spatial scale. Right, so the second type of model will be the data drive model, like some linear model or more complex, like machine learning model. So it's the model that I'm working on in my team. So for all this model, you will fit this model with some data. So it will be like, for example, the surface reflectance for sure, or other type of data like radar data, but also every other data that you can have, like from the ground measurement, like the temperature, the soil texture, soil moisture, or you will get some parameters like from numerical weather model to know, for example, what is the temperature at 2 meters from the ground. And then the last final part, when you build your model based on some statistical data and available data, you have to train this model and to validate this model. So that is the most important and, let's say, a tricky part, is because the size and the spatial resolution of this training validation dataset will determine what method you are going to use and what is the uncertainties associated with your model. So I've been working in my team. Actually, we have been working for more than a decade on yield models. This yield model is called ARYA, and it works with MODIS data and now VIIRS data at country and subnational level. So I will quickly introduce this model. So the first step of this model is to build a crop mask. A crop time mask. So here it's an example of different crop time masks that we built using MODIS 8D composite over several countries, like in Europe and Argentina, Australia, and the USA. And we built an early in-season crop map to, like for winter wheat, for example, like at the beginning of the years around March, April. Because we want to do a yield forecast for the current year, right? But if you don't have any crop time mask, because it's like Christian was talking before, it's complete other subject. And you can already find some data set with some crop time mask, like from ESA or the USDA CDL, GRC, LUCAS, or you can already use this data set. They are not in-season crop mask, but you can already use that to build already and train some yield model. So once you have a crop time mask, so here it's above Ukraine, you can see, so it's a winter wheat crop mask for 2021 built with MODIS. You can extract for over every oblast, over every pixel, the parameters that you want. So from surface reflectance that you want. So in ARYA, we use the vegetation index, the DVI, and we extract the DVI over every pixel for each oblast, because the oblast in that case will be the spatial unit of my yield dataset. So I have 20 years of yield data for each oblast. So then for each oblast, I will extrapolate these spectral indexes to 100% of winter wheat to unmix the signal from the other proportion, what is not winter wheat inside my pixel. And I will get a value of DVI with a standard deviation associated corresponding of the variability of the DVI inside the oblast. So as you can see, you get one value of DVI for every oblast. And associated with the DVI, you can estimate, in that case, we estimate the GDD, which is the growing degree day. So it's the accumulation of temperature, which is good parameters to follow the phenology of the crops. So with these two parameters, we plot a Gaussian fit between the DVI and the GDD. And from this Gaussian fit, we extract two predictors, which is a peak and the width of the Gaussian fit. So I will not go further in detail in ARYA model. You have a paper on it if you want to know more about it. You can find the paper. But we have other predictors in the ARYA model. That are the main two predictors. So once you have your parameters, you will build a multilinear regression over using your predictors and the D-trend yield over the dataset. So here it's an example over the side. Okay, whatever. So we remove the trend of the yield and to actually keep only the variability between years and train the model only the variability and for the model to don't learn about the trend. So we calibrate the model on the past data and we get the coefficients of the different predictor. And in operational, actually, we will apply this coefficient to the current year. And every week or every time we have a new data set, a new spectral data coming up or new temperature data, you can get a new yield forecast for regional level, in this case for each oblast. So another very important part of any yield model is to understand what are the uncertainties linking with your yield model. So in ARYA, the main source of uncertainties come from the crop mask and the ARYA estimation. So first, the ARYA estimation, it's because to estimate the national yield in ARYA, we use the yield forecasting at every oblast level that we're weighting with the ARYA estimated at oblast level. But in operational, we don't necessarily have this planted area for each oblast because there is no official data set, or it's not yet released, or there isn't any reason, or in the case of Ukraine, because of the war in Ukraine. So we cannot get necessarily the planted area for every oblast. So you will use what you can. So for example, we use sometimes the 5 years average for every oblast, or we use a pixel count ARYA estimate from the pixel count weighting our different oblasts. And that is one of the biggest source of uncertainty for the national level. Another source of uncertainty comes from the crop time mask. And for example, here it's a crop mask that have been done by the Harvest team 2022, showing a different type of crop. And as you can see here in yellow, you have the fallow abandoned field in Ukraine due to the war. And so it's important to remove this pixel from the signals that from the DVI that I'm extracting to remove these fields that were not cultivated to unbias a bit my signal. Another important point is to have, as my model, this model, I mean, is calibrated over the 20 past years. It's important to have similar crop mask over this 20 past years built on the same model, by the same method, to propagate the error from a year to another, and the yield model will learn this error into the calibration. So another uncertainties that we are taking account in ARYA yield model, it's the uncertainties due to the variability of every indicator inside the oblast. So as I was showing you, for example, for the DVI, we have a huge variability inside the oblast because the oblast is still a very big area. And so we want to actually be able to give at the end of the model for the yield forecasting new per yield estimation and estimates and a lower yield estimate. And so we apply to every DVI value the standard deviation. I didn't show it here, but for the DVI, but also for the GDD. And we can get two new Gaussian fit with two predictor for the peak and the width, and we can get like that yield value, three yield forecasts. The actual forecast and more the maximum and the upper and lower value. So when we move from the time step, so here is the day of the year 120 to the day of the year 125, you can see actually that the standard deviation decrease, and so the uncertainty decrease over time as we approach actually the peak of the growing season. So now the evaluation of the yield model. So we evaluate ARYA over the 2023 years of Moody's data. So that is just an example over the USA when we evaluate ARYA. So you have the average of the relative error at county level and the error, the RMSE actually, so the root mean square error over time. So we get an average of error at national level around 6% and at subnational level around 20%. So we can see that the error increase a lot between national and subnational level. And what we can see too, it's very different from a country to another, countries to another. And that is due because, for example, in the Midwest, we have some years with a big drought, or especially big frost event that were damaging the yield and the wheat, I mean, at the beginning of the season. So with this model, then after having building this model, we creating an operational version of this model that is running, actually running now for many different countries, but especially over Ukraine. So we are monitoring the production in Ukraine during the war. So you can see on the right the yield forecasting over time, like from the day 110 until the day of the year 220. So that it was like around May or something, May, June of 2022 for the free territories and the occupied territories. And so we estimated that a loss of production around 7 million of ton of winter wheat from the occupied territories. And knowing that in average in Ukraine, they produce of winter wheat around 25 million of ton. So a second important aspect of yield forecasting is when you have an operational model, it's important to understand what will be the impact of integrating a new sensor. So as you know, Moody's is going to be the decommission very soon, in the next few years. And so now we are going to use VIIRS instead of Moody's. So I just conducted a short study. I'm not going to go more in detail, but it's I'm writing the paper right now. So it's just a study to see how the difference in spectral band and in of coverage impact actually the yield for different crop over the USA. And so it was interesting to see that the definition in that case of the cloud flags, so actually the data that we can use is very different between VIIRS and Moody's and has a huge impact of the occurrence of each category and the clear category, especially when you can actually use it inside the models. So I evaluated the difference between Moody's and VIIRS in ARYA, so that it's over Ukraine, I think, calibrating on 12 years of data instead of 20 years, and validated leaving 1 year out. And I saw a bit of discrepancy between VIIRS and Moody's from changing at national level and subnational. I lost like 1 or 2% of accuracy. So now the question is, as we see that the error increased a lot from national to subnational levels, how to improve the yield model for smaller spatial units, so at county level or at field level or even smaller spatial unit. So one of the methods that I am working, the first thing that I did, it's I have a kind of short project with the USDA and the USGS over a farm, an experimental farm in Maryland, so very close to where we are now. They have around like 33 fields in productions with different kind of crop and corn, soybean, wheat, grain from 2016 to 2023. So you can see the distribution of this crop. So the first question that I asked myself is how the ARYA method could perform at field level. So I use HLS data at 30 meter spatial resolution and the DayMed dataset that you have several methodological parameters at 1 kilometer spatial resolution to extract the DVI or the DVI parameters and calculate the GDD over all these different fields. So that is just an example over one field. So what you can see first in the figure in the middle is like I had many issues with the cloud filtering at that scale. With 30 meter of resolution, even applying the cloud mask, it couldn't properly filter all the clouds and the shadow at this scale. So I manually remove all the clouds, the shadow for every field. So on the right, you can see the same method as ARYA. So I apply on the smooth and DVI vegetation index. I apply the Gaussian field and I could get the peak and the width of the Gaussian peak. And I did that for every field, for each crop. And I got this result living 1 year out, and we can see that the result decreased significantly from ARYA at county and national level to field level. And especially you can see that we underperform at high yield values, even if the results are like in the average of the state of the art now. If you read other paper on yield at field scale level, they will be around this kind of result. So why that is happening? So that is a very short study that I made, another study over some crop. It was in Iowa. I have some crop yield over some field. And I look at the decrease of accuracy in function of the spatial resolution. So on the axis, you have the spatial resolution that I aggregate inside my film for 30 meter to 900 meter. And on the vertical axis, you can see the coefficient of determination that shows your correlation, how good your model here. So that it was for different parameters and for different model and for different type of data. So it works, I look at for spectral band and I look at using SAR data, Sentinel-1. So building a yield model using different kind of parameters. And what I observe, that is something that is commonly known, that more you aggregate your data, your yield data, better your model will be, is able actually to predict the yield. And why? Is because you reduce drastically, so it's like the black curve, you reduce the variance of the yield inside when you get a closer spatial resolution. So it makes easier to predict a yield with low variabilities and a yield with more variability. So to assess this issue, what we have to do is we need to introduce more variance in the dataset to capture yield variability. So you need to introduce more type of data to explain the yield variability. So one of the first methods to do that is to mix actually different type of data. So I had this study on Arkansas over 258 fields, was to see if we could find interesting parameters, can follow the phenology by mixing SAR and optical data. So I had different SAR data. So I have 3 different type of radar data and 2 different type of optical data for 3 crops, rice, corn, and soybean. And so I'm not going to enter in detail again in this study. So you can find the paper if you are interested in this kind of things. But what we can see is that we could see that we identify interesting parameters from SAR data. So it is entropy and alpha parameters that will show the texture of your fields, the texture of the plant. So on the color of your color bar is a value of the GDD, of the growing degree day. And so it shows actually the growing season. So when it's blue, it's the beginning of the season. And when it's red, it's the end of the season. And so you can see on these two graphs. That one on the left is for the L band, that is longer frequency, and on the right is the C band. You can see that these two radar see the plant, see the crop to two different ways. So first, they start by seeing the surface scattering. That is, the surface scattering is the most important parameter. So what they will see the difference in surface, like when the growing season is starting. And more you go through the growing season, they will see, they will go and the radar will go to see more what is the volume of the plant. So it will be the difference of size between fields. For the A band and not for the C band, the A band will be able even to see through the rice, going through deeper, like multiple scattering, so to see the difference in rice inside the field, which is not the case for radar SAT2, the C band. So just to evaluate this kind of all parameters, I apply a random forest regression model for the different crop over a bunch of parameters of optical and radar that I found them useful. And by using different type of parameter, we were able to improve a lot the yield forecasting, the yield estimation, by reducing the relative error when combining the SAR data and the optical dataset. So this study, I suppose, the goal of this study was to understand what kind of parameters could be useful and at what kind of time of the growing season, along the growing season. But after to apply this method, we need a much bigger data set actually to train the model and again to validate over different country and different type of area. Another thing that I would like to highlight, it's something important that I saw in the small study. It's the crop cultivar. So the most part of the study, we use the yield data set that is mixing a lot of crop cultivar between crop varieties. So here it was in this small study, we had different cultivar for corn, for soybean, and for rice. And by unmixing this cultivar, for each cultivar, you have very different yield average and standard deviation, very distinct because all these cultivars have different phenology. So by mixing them, you are mixing different phenology that don't belong together. Like for some cultivar, the growing season, the first part, like the emergence, will be much slower than another cultivar. So you cannot mix all these cultivar together. And by unmixing them, we could improve in the yield estimation for each varieties. So there is some new study coming up right now to try to map, actually, to create some crop type map per cultivar. But that is a huge challenge, as we can imagine, because a rice with different type of cultivars still look like rice. So it's another challenge that some people start working on that. So I will finish with this last slide. Finally, once we can look at the yield forecasting at field level, but we also can look at the yield forecasting inside the field, at sub-field level. So that is a project that I have with the USDA and USGS again over the same bark field to identify, to combine different type of data sources, so like landform, soil texture, but also farm management information, specific on every field, to be able to identify how to manage in real time a farm and a field data set. So the question that we are asking in this project is what kind of yield model we should build at that scale. So should it be a yield model like ARYA based, or should be a yield model maybe based on some classes of potential of yield inside the field? So that is a project that I just starting working on it. So just to finish, I would like to highlight some important point about yield from my point of view. So the first point is like that optical satellite sensor, like MODIS, VIIRS, have shown being very useful actually to create a yield forecasting model. You can find many papers with different methods using this data set. But this data set, if you go at local scale, will show some limitation. So that's why it's important now to try to integrate a new technology for forecasting, like mixing some different type of data, or now you have some new instrument coming up like hyperspectral data, and we expect that they will improve the agriculture monitoring in general. Another important point is to push forward for every special agency, hopefully, to keep having long-term and large-scale data sets, as these data sets are very important to actually train any model, and more important than training, but even validated any model before actually giving an operational yield data. And that's why I come with the data quality. So it's important to actually assess the quality of every data, and that it is the yield data set first, when you get a yield data set, to assess the quality of the yield data set, to assess the quality of the data, and to compare different sensors together to understand how the uncertainty are propagated inside the yield model, and to be able to extract an uncertainty when you get the yield forecasting. And the last point I would like to highlight to, it's about the score evaluation that I will be working on this project at a sub-field level. It's what kind of score are pertinent to share with government entity or farmers or stakeholder, and even among the research community, what kind of score is important for us. As for example, how is it important that my coefficient of determination, my correlation, will move from 0.7 to 0.8? What is the impact in terms of productions, And finally, when you talk with a farmer, what kind of information the farmer want to know? Does they want to know yield, precise yield number, or would you like more to know about what is the probabilities and his yield will be higher this year than the 10 past years, or something like that? So is this kind of questions that I think are important when we build any yield model. Yeah, thank you.
Thank you so much, Natasha. Thank you so much. That was great. We open the floor for the questions, and yeah, you can use the Q&A section or the chat, actually. Molly.
Yeah, let me ask a question. Natacha, so interesting, fascinating. In sixth grade, we have looked at the subfield analysis. And what we find is the farmers that we engage with are very interested in it, but they have no idea what to do with the information. And even the, agronomists who are working across 500 or 1,000 fields also. So it's really not, and in a lot of this, it's not we're in remote sensing, we're like way ahead, and there's no one there to catch the data. So what's your experience in acres with that problem? I mean, do you feel big pressure to provide more and more accurate information and people don't know even what you provide them? Or what's your experience with that?
Yeah, thank you for the question. I think it's a very important key to think about when we build a yield model, and even for the future of a yield model forecasting. So I will say there is different, depend of who you are talking to, and I will talk about the harvest point of view or the acres point of view. So from the harvest point of view, that is more like a global scale or like a national or subnational scale, talking with government. What they want to know, it's for them they want to have a yield number, but what they want to know is the uncertainties of this yield number, and that there is a kind of huge pressure about the uncertainties, because when you have even a small uncertainty in the yield multiplied by a huge planted area, become a huge uncertainty is crop productions, right? So it can be a million of ton actually of production of difference from 1% of uncertainties. So that it's an important question. That's why I will say that in harvest, people are more working on improving the yield at a subnational level, and thinking about how to improve the uncertainties. And to improve the uncertainties, there is different ways. There is for sure work on the crop mask, the planted area, to know exactly what was planted, what was harvesting too, because that is a good question. We know sometimes what is planted, but we cannot capture what is harvesting necessarily. So some people in harvest are working on that. And improving the yield model, so that it's an important aspect, especially in climate event again. So for example, with ARYA, this model is based on so linear model, machine learning model or whatever, but learning processes over a statistical data set. And our statistical data set is too small to capture for the model to learn climate event. So that is another aspect to work on it, how to mix maybe different type of data set to maybe over the world to predict one country, but to have more actually climatic event. It's one aspect. You can find different way to work on that.
You know, and just when, you know, we found that we totally missed this huge increase in yield in across our 300,000 hectares in Brazil because it was so big and it was not in our data set at all. We had no idea it was possible to get 5 tons per hectare.
Exactly.
We were proposing, we thought it would be 3 tons. And they're like, no, we all got 5 tons. Where have you guys been? When is the last time that happened? Well, never.
Never, exactly.
Exactly. So that is the problem. We don't, our data set was stuck at 3 because nobody ever reported anything greater than that. So you can't make this stuff up. It's so, so hard.
So it's the same issue in ARYA model. It's like we can see the variability over from a year to another. And when you have a higher yield or lower yields than the trend, let's say much higher or much lower, we see the variation, but we don't capture the amplitude of the variation. And to capture the amplitude exactly, it's to increase the data set or to create maybe some mix, maybe some crop yield modeling, crop physical based model with remote sensing data. Like I've seen take some I've seen modeling and mix with remote sensing data and do some kind of case study like that. So that is another thing that we're thinking about. So to answer the other question, like from the point of view of acres, so that is very interesting because now more and more I'm talking with farmers, just the beginning of the project and for sure, but I can think that but some of them depend, some doesn't know anything about it, but some are meeting with us. Now they start to understand what we are talking about and what is an uncertainty of 5%. And so what some farmers are telling me is like, oh, sometimes what I would like to know is to know if finally the yield over this field will be very lower than usual, much worse than usual. Because if this field doesn't underperform by a lot, I will just give up on this field and maybe put more care to another field that I can see then the yield will be better or at least in the average. So it's more this kind of information that maybe they would like to hear from us. So that's why I was talking about probability, because it will be maybe what is better year on a worse year, like for farm management. But that I think is really an ongoing talk that we can only improve by experiences directly on the field with the farmer, the yield model. So that hopefully we will be able at some point to do this kind of experimentation. Yeah. Thank you.
Thank you. You have a question in the chat actually, if you can see it.
I cannot. What is the actual accuracy and spatial precision of your satellite solution, like it was there, when applied to and desert region around the world? So actually, it's a very good question. And I don't have exactly the answer because I never apply for an ARYA around above desertic region. So I wish I could have a data set actually to apply ARYA on that. My main limitation in any of my study is any available data set to train the model and to validate this model. I will say that over desertic region, I don't believe that the dataset region will underperform other type of region, because what it will be the most important, it will have to have an accurate crop time mask over any region of interest. Once you have this accurate crop time mask and enough long data set, like maybe 10 years of data at some like regional spatial scale with an accurate crop time mask, you can train this model, and the model will learn from different type of region. For sure, after, I think if we want to improve the model, we need to integrate inside the model more like maybe some weather parameters. That's what we are working in. But it's not, what I saw in ARYA, you cannot just add another predictor, like saying, okay, it will be soil moisture. Because actually, the soil moisture will impact the yield. It's not completely linear. It's not because you can capture soil moisture every day that you know how it impacts the yield. It will depend, for example, if you have a drought. If you have a drought for 10 days, maybe it will not impact the yield because it's a specific time of the growing season. Maybe if you have a drought for like a month, like we know that it will impact the yield at that time. So it depends really of on how you integrate this kind of weather parameters inside the yield model. Yeah.
Oh, I think, oh, you have other questions.
What is the impact of cloud period, and a combination of weather and remote sensing can be used to help this yield prediction of cloud period? So when you talk about cloud period, I guess you talk about shadow, maybe? I'm not sure to understand the question, actually. Can be used to help the yield prediction. So yeah, for sure, the combination of weather is essential to help the yield forecasting. That for me is it's absolutely certain. It's just not sure how for now we integrate the weather prediction with the yield model. So we are working on that, especially on soil moisture and evapotranspiration. That are these parameters are shown very important impact on the yield over the USA, and we are working on timeline and growing stages, key growing stages during a climatic event to see how we can improve the yield by integrating this kind of weather data. Have you worked with field model for perennial crops such as coffee or cocoa? What factor or variable do you think contribute to uncertainty in this model? So I love the question. I never worked with any fruit trees or nut tree with the ARYA in the yield model. And actually, it was one of my questions is, can we actually use ARYA model or any yield model to predict over the production over some bushes? So for now, I don't have the answer at all. I don't know because the bushes, right, is not necessarily the fruits like will grow over a bush is not necessarily linking with the shape of the bushes, with the color of the leaf. So that it's a really, complex question, but I never try it for now. Yeah. We have developed a solution that connect agronomist and farmer, but it's challenging to obtain reliable local data to train AI model. Do you think combining satellite data with localized ground data could significantly improve the accuracy and reliability of agriculture prediction, especially in arid region? To obtain reliable local data. Okay. So what I don't know what you call by with localized ground data. So is it ground data of yield ground data, or is it like ground data like more temperature or weather data? I'm not sure about it. So what I will answer about that is so I read some new paper about it, and now as the data set, the size of the data set, and it's very challenging to get any data set, reliable local data set for sure. Some people are working now to build models using regional data sets that are usually more reliable than local data set to actually train local yield model by doing a kind of downscaling, a model transfer from spatial resolution to another spatial resolution. So maybe you can look at this kind of paper to look at how you could maybe train some model at a higher spatial resolution to train your local spatial resolution. But in any case, you will probably have an issue to validate at least this local yield model. You will still need a yield data set, I guess. Above, I would say that without any yield data set, if you maybe take a country that you already have a lot of other data, right? Like the USA or any other country, like a more dry country, and you have a data set. So you can train maybe a model on this data set and find some relation. And with this mathematical relation, you will maybe be able to apply this method on another country, knowing that the accuracy will not be as good because it's very localized. Any model for now is very localized. So that's another aspect that we should train the model to be less localized. So when you, so you will maybe be able to see some variability of the yield, like higher yield, lower yield, medium yield, but you will not be maybe not able to say, okay, this is the yield value. You're not able to say, okay, I have 7 tons per hectare, but maybe you will see that I have a high yield or a low yield. Yeah, exactly. It depends on the agronomy and accuracy. Yeah, it depends completely of the accuracy of any of your data sets, for sure. The yield data set is one of the biggest source of error. Yeah.
Well, that was super interesting, and I'm very happy to see that all, I mean, many people like that are directly concerned of the discussion are here. I mean, I'm very happy to see that the EOS, the A are here also. So, Morad, you can reach out directly to
Yeah, sure.
Anna.
Please just don't hesitate if you have any question or if you want to continue the talk with more specific subject, just don't hesitate reaching out to me by email and we can just schedule a call or whatever. Yeah.
Thank you.